Hello everybody and welcome back. In today's video we're going to finish off the 2008 Friar Contest. We've come a long way. We're up to question number 4 and that's the final question on this Friar Contest. So how about we take a look at the last question. Alright. When the first 30 positive integers are written together in order, the 51-digit number x equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the way up to 30 is formed. Alright, so I assume we're going to have questions about this kind of a number. One where we've concatenated a whole bunch of the positive integers in order. Okay, A part. A positive integer that is the same when read forwards or backwards is called a palindrome. For example, 1, 2, 3, 2, 1 and 1, 2, 2, 1 are both palindromes. Because no matter what order, left to right, or right to left that I read the digits in, I'm saying the same numbers in the same order. So left to right here is 1, 2, 3, 2, 1, and then if we go back right to left, we get 1, 2, 3, 2, 1. That's what makes it a palindrome. You have hopefully seen palindromes before. They come up on contests from time to time. So it's a good concept to be at least passingly familiar with. Determine the smallest number of digits that must be removed from x, so that's the large concatenation of positive integers, the smallest number of digits that must be removed from x so that the remaining digits can be rearranged to form a palindrome. Justify why this is the minimum number of digits. Okay. So, palindromes can either have odd length or even length. Right? Here we have one of odd length, of length 5, 1, 2, 3, 4, or 1, 2, 3, 2, 1. That's 5 digits, and here we have one that's even, 1, 2, 2, 1. So what we're going to do is we're going to realize that we need to pair up digits, and let's write down our explanation as we're explaining it out. Right? Every digit to the left of the middle has a corresponding duplicate on the right side, from the right of on the right side of the middle. So in both the examples we're given, we have duplicates. So if we want to make a palindrome, what are we going to need to do? Well, we're going to need to have pairs of numbers. So this means we're going to have an even number of 1s, an even number of 0s, an even number of 8s, except possibly whatever digit is in the middle. Right? So if a 5 is in the very middle, we're going to have an odd number of 5s. Okay. So it might help to figure out, well, how many of each type of digit are there? Okay, so if we go back to our actual number, we could count out how many zeros there are. There's 1, 2, 3 zeros. And we could probably make a little chart. I don't have room to do a vertical chart, but maybe we can fit in a horizontal chart. That's a terrible horizontal line. Genuinely makes you appreciate why I usually draw vertical lines. So there are 3 zeros. We'll have 1s, we'll have 2s, we'll have 3s, we'll have 4s, 5, 6, 7, 8, and at the very end we'll have 9. Okay, well, how many 1s are there? Right, we can either sit here counting out because we have the actual number, or we could be a bit clever about it. In the 20s, there's just going to be the 1 for 21. We don't get into the 30s at all. In the single digits, we have 1 there, and we have 1 in the units digit of 11. So that's 13 ones. And then, for the teens, each teen starts with a number 1. 10, 11, 12, 13, 14, 15, these all start with the number 1. So there's going to be 10 more copies of 1 there. So that's going to give us 13 ones. By the same reasoning, we're going to get 13 twos. Well, how about 3s? We have 1, 2, 3, and then we have a 4th one because we start with we end with 30. We start the 30s. We end with 1, 3 for the 30. So that gives us 4 of those. Now we don't get into the 40s at all. So the number of 4s is going to be the same as the number of 5s, the same as the number of 6s, all the way up to the 9s. 1 in the singles digit, 1 in the teens, and 1 in the 20s is going to be 3 of each kind left. And if you wanted to, you could probably double check this by adding it up with a calculator. But we have 7 3s, so that's 21 plus 26 for the 1s and 2s. 26 plus 4, that's 30. So 30 plus 21, that's 51, and we were told it's a 51-digit number. So we haven't missed anything. So notice that we want all but one of these groups of numbers to be even. We want maybe the 2s are even, maybe the 6s are maybe the 2s are odd, maybe the 6s are odd, and everything else needs to be even. And we don't have that. And we're asked to remove digits. So we need to basically remove one digit from each of these categories, except 3. 3's fine the way it is. 3's even, so that's good. And we're allowed to leave 1. If we have a middle digit, we could leave the zeros as odd, and then we'd know 0 is the middle digit. Okay, so we have 9 groups that are odd. We need most of these groups to be even, so we can have one odd group. That's fine. So 9 groups that are odd, we need to make 8 of them even. If you have a group of an odd number of marbles, you just need to remove one of them to get an even number of marbles. So we have 8 groups that need to be made even out of the 9 groups that are odd. So the quickest way to do that, to make an odd group have an even number in it, just take one of them out. So 1 out of each of the 8 categories that we're choosing to make even. We don't have to pick which categories are which. Yeah, so take out 8 of them, and that makes 8 of the 9 groups that are odd even. And so along with the 3's, then we'll have 9 even groups and 1 odd group, and that odd group will give us what the middle digit is. Yeah. So that's A part. The answer is 8 digits, and we have justified why it's 8. Okay. B. Determine the minimum number of digits that must be removed from X so that the remaining digits have a sum of 130. Justify why this is the minimum number of digits. Now, a little thing to note here, we're not talking about palindromes anymore. Okay, I believe that's in the next part of the question, in C part. So, we're just trying to get the remaining digits to have a sum of 130. So we're not rearranging them, we're not trying to count the number of ones and twos and odd groups or anything like that. We just want the sum of the remaining digits to be 130. Well, what's the sum that we have now? That'll tell us sort of how many and what sort of number we need to remove. So we had 0, 3, 1, 13, 2, 13, 3, 4, 4, 5, 6, 7, 8, 9. Each of these groups had 3. So if we want to figure out the total sum that we have at the start, what's the total sum of the digits of x? And that'll tell us what sort of difference we need to make. Well, we have 0 3s, and so in total they contribute 0 to the total sum. We have 13 1s. That'll give us a total of 13 being added. We have 13 2s. That'll give us a total of 26 being added. 18, 21, 24, and 27. Okay, and if we add all those up, 13 plus 26 plus 12 plus 12 plus 15 plus 18 plus 21 plus 24 plus 27, we get 168, which is the number of hours in a week. Fun little number association there. We want 130. So we need to get rid of as few digits as possible that add up to 38. Okay. Well, what's the best way to do that? Getting rid of all the 9s knocks off 21 right away. And then if we get rid of an 8, that brings us down to, so from 38 we got rid of 27 of them, so that's 11. Subtract an 8, then we need to get rid of a 3, and that would give us a total of 5. But we need to justify that a little better. So, all 3 9s, 1 8, and 1 3. So we know how to do it with 5 digits. We will show that this is the minimum number of digits if we can show that there's no way to do it with 4 digits. Okay. So if we were to somehow be able to do this with 4 digits, all our 4 digits would be less than or equal to 9. Now, not all 4 digits can be equal to 9, but that's really neither here nor there. The point is we have an upper bound on what each digit can be. It's 9. And if we have 4 9s, then at most the sum could be 36. Now, if we go back to this table, we know there's no way to actually get 36. You'd have to have 4 9s, and we only have 3 9s. But the point is, we're just trying to show that no matter what you do with 4 digits, you can't get to 38. And so, if at best each digit is 9, even if that doesn't actually reflect our reality, then at best the sum is going to be 36, which will never ever be 38. So we'll never get enough. So to get 130, we need to remove a minimum of 5 digits. And there's probably a couple ways you can do it. It's not just the 3 9s, the 1 8, and the 1 3. You could probably, I don't know, 3 8s is 24, and then remove a 9, that's 33, and then you could remove 1 5. There's probably a lot of ways to remove a minimum of 5 digits. But we know it can be done with 5, and then we showed it can't be done with 4. So we justified why 5 is necessarily the minimum. Okay, C part. So it's a slightly bigger number than x that we're dealing with here. When the first 50 positive integers are written in order, the 91-digit number 1, 2, 3, 4, all the way up to 50, which we're calling y, is formed. Determine the minimum number of digits that must be removed from y so that the remaining digits have a sum of 210 and can be rearranged to form a palindrome. Once again, we need to justify why this is the minimum number of digits. Okay, so it's a combination of A and B. We've learned from A that we need to sort of have pairs of digits. So we need to have an even number of 1s, an even number of 9s. And you can have at most one group of digit, one type of digit that has an odd number. So maybe an odd number of 3s in our palindrome. And from B part, we learned a little bit about removing digits just to get a specific sum. Okay, and we know how to justify why there's a minimum number of digits for that sort of thing. Alright, so just as before in A, and although we didn't actually do it originally in B, we used our work from A, we need to figure out how many 1s, how many 2s, how many 3s, how many of each digit are we already dealing with in Y. That'll tell us what we need to pair off, and then we can start worrying about getting a sum of 210. Oops. All right. So we know I have 91 digits here. So let's take a look at the zeros. There's going to be 5 zeros. 1 for 10, 1 for 20, 30, 40, and 50. So 5 zeros. Okay. We go up to 50. So the 6s, the 7s, the 8s, the 9s, they're all going to be the same. There's going to be 1 for each single digit, 1 in the teens, 1 in the 20s, 1 in the 30s, and 1 in the 40s. So that'll also be 5. Now we end at 50, so that's 1 extra 5, as opposed, and in addition to the one we have in the single digits, the one we have in the teens, the 20s, and so forth. So that's going to be 5 plus 1. That's going to be 6 copies of 5. And just as we saw in part A, the 1s, the 2s, the 3s, and the 4s, well, it's going to be the same number of each of those. Okay, so we could go back and try and work it out and say, okay, well, there's a 1 in each of the ones, the knots, the teens, the 20s, the 30s, the 40s in the single digits, and then 10 additional ones for each of the teens. But we could also say, well, we know there's 91 digits, and we know that 5 plus 6 plus 5 plus 5 plus 5 plus 5 digits are already accounted for. That gives us a remaining number of digits of 60. Well, 60 divided evenly by 4 is going to be 15 digits each. Okay. So there's two ways we can do it. Doesn't really matter. The point is we fill out this little chart. So once again, we have exactly one even group and we have a bunch of odd groups. And we want to make most of those odd groups, all but one of them, into an even number. But at the same time, we're also trying to get a specific target sum. So what is that sum? Well, we have 5 zeros, and that gives us 0 for our overall total. 15 ones, 15 twos, 15 threes, 15 fours, 6 fives, 5 sixes. We have 35, 40, and 45. Okay. 15 plus 30 plus 45 plus 60 plus 30 plus 30 plus 35 plus 40 plus 45. So we get 330. Okay. And we want to bring that all the way down to 220. Sorry, to 210. So we need to get numbers to be in pairs. So each one of these numbers is we're going to have to remove a 9 to get 4 9s, so that we can have 2 9s on either side of the middle, for example. So in addition to removing numbers, we also need to remove the numbers so that the sum of the removed numbers is 120. Okay. So there's no reason to remove zeros. They don't bring our sum down. You know, we could have 5 zeros, we could have 50 zeros, we could have 0 zeros. We'd still have a sum of 330, and we need to get that down to 210. So if 0 is going to be our leftover odd group, 0 will be the middle digit. The question isn't asking us for how the numbers need to be arranged in our palindrome. That's fine. But we're just clarifying that 0 is going to be the middle digit. That's why 0 is our leftover odd group. Okay? The reason we do that is because we don't need to remove zeros. That would make no sense. It wouldn't bring our sum down. And so we'd remove a bunch of zeros. We'd still need to remove other numbers to bring our sum down. So we need to remove at least 1, 1, 1, 2, 1, 3. The 5s are already even, so that's fine. 6s, 7s, 8s, 9s. So that's 8 digits we're removing already. And those digits have a sum of 1 plus 2 plus 3 plus 4 plus 6 plus 7 plus 8 plus 9. And that gives us 40. So we need to make up a total number of 120. We have removed 40. We still have 80 to go. All right. Incidentally, if this sum had been more than the difference we were trying to make up, maybe it was 38 like last time and we got a sum of 40, we would have to go back and re-examine whether or not it makes sense to remove a 0. But because the number was 120, it was so wildly huge that we could easily say 0 is going to be the middle group, and we can definitely remove at least 1, 1, 1, 2, 1, 3, all the way up to 1, 9, and still have a sum less than 120. So we still need 80 to go. So to keep our palindrome going, we have to remove pairs of the same digit. We can't take out 1, 9, because then we have 2 odd groups. So we need to keep our even groups even. So we're going to be removing pairs of digits. So if we want to make 80 and we're doing it in pairs, then we need each pair name. So each, if we're removing 2 9s, we would say 9, and we need to add up to 40. So we've already removed 1 9. How many 9s do we have left? 1 9, so that'd be 4 9s. So we'd be able to have removed 2 pairs of 9. So 2 9s, and we have 4 8s left as well. So 40 minus 18. Then we could get 2 8s. So that'd be 40 minus 34. And 1 6. Okay. So there we had to remove 5 digits, 5 additional pairs. And that's 10 more numbers. So we already moved 8 digits, 5 more pairs, 10 digits. So, same question as in B part. Could we have done it with less? So if we had 4 pairs, at best they would all be 9s. So pair of 9s, pair of 9s, pair of 9s, pair of 9s. I have no idea how I ended that sentence. At best they would all... Okay, so I want to write B. Four pairs of 9s, well that's actually 8 9s. That's 72, which is less than 80. And that tells us we had to use 5 pairs, and we got 120. So we needed to remove exactly 18 numbers here. Right, just to get it in the state of a palindrome, which is at least one group, or at most one group odd and all the rest even, we had to remove 8 digits. Then to get our sum of 120, and to keep it a palindrome, we had to remove pairs. So the pairs had to total up to 80. So the numbers in each pair, not counting both numbers in the pair, had to be equal to 40. Okay? We could do that with 5 of them, the 2 pairs of 9s, the 2 pairs of 8s, and 1 pair of 6s. That would do just fine. However, we then had to ask, could we do it in less? We still need pairs, because we need to keep our palindrome. So could we do it in 4 pairs? No, we couldn't. We justified our use of 5 pairs, which is 10 digits being removed. And we already had removed 8, and that gives us a total of 18 digits. And I think that's all we were asked for. Sum of 210, form a palindrome, and we want the minimum number of digits. So that's it. We're done the last question on the 2008 Friar. I think it was a good paper. But leave a comment telling what you thought of the paper. How well did you do when you tried it? And, if you want more Friar papers, you can feel free to subscribe to my channel, because I keep making these. And, yeah, that's about it. I'll see you guys in the next video. If it's another Friar, if it's another contest altogether, who knows? So I'll see you guys then.